For years, long-haul flight meant 4 engines and visible redundancy. Today, it means 2 engines doing far more work. Behind that shift are 2 aircrafts, the Boeing 747 and the 777X. The Boeing 747 was born in the late 1960s, when long-haul travel was expanding rapidly and engine reliability was still limited by the technology of that time. 4 engines were incorporated into the aircraft, and early variants were powered by Pratt & Whitney JT9D, GECF6 and Rolls-Royce RB211. These engines were revolutionary but conservative by modern standards. On the final 747 variant, the 747-8, Boeing moved to the General Electric GEnx-2B engine that promises better fuel efficiency with lower emissions as well as reduced noise. Fast forward to the era of the Boeing 777X. The world it enters is defined by decades of engine reliability data and strict certification standards like extended range twin-engine operational performance standards. The 777X is designed around the GE9X engine, which is built specifically to make ultra-long-haul twin-engine flight routine. The 747 assumed engines would fail and planned around it, while the 777X assumed engine failure would be much more rare. The most obvious difference is also the most symbolic. The 747 uses 4 engines. The 777X uses 2. But that difference is more than just about saving weight or fuel. A classic 747 could lose 1 engine and continue flying with relatively modest performance penalties. Losing 2 engines was still survivable in many scenarios. That redundancy defined its safety philosophy. The aircraft demanded availability from its engines far more than perfection. The 777X takes the opposite approach. Each GE9X engine is designed to be powerful enough that the aircraft can meet all performance requirements on just 1 engine if necessary. Certification testing includes extreme single-engine scenarios at maximum weight and worst-case environmental conditions. The aircraft does not rely on redundancy through quantity, it relies on redundancy through capability. Before we move forward, here's a question for you. When you think of long-haul travel, do you picture 4 engines or 2? And do bigger engines mean power or efficiency for you? Drop your thoughts in the comments below and we'll discuss this later in the video. One of the most striking visual differences between these engines is fan diameter. Early 747 engines like the JT9D had fan diameters around 93 inches. Later variants, such as GEnx-2B on the 747-8, increased that to about 104.7 inches. The GE9X on the 777X pushes this much further. Its fan diameter is approximately 134 inches, which makes it the largest jet engine fan ever certified. That massive size allows the engine to move a far greater volume of air at lower velocities. This matters because modern efficiency comes from accelerating more air gently. The result is higher bypass ratios. The GE9X operates with a bypass ratio of roughly 10:1, compared to around 5:1 for early 747 engines like the JT9D and 9:1 on the GEnx. More bypass means less noise with lower fuel burn, and therefore better efficiency across long cruise segments. But this scale comes with challenges. Larger fans mean higher structural loads along with complex containment requirements and tighter tolerances for blade deformation. Solving those problems required materials that simply did not exist when the 747 was designed. The 747's early engines relied heavily on titanium alloys and nickel-based superalloys. These materials were state-of-the-art at the time and remain important today, but they limited how hot engines could run and how much pressure compressors could tolerate. On the later 747-8, the GEnx-2B introduced more advanced materials like composite fan blades and higher temperature nickel alloys that allowed higher operating pressures and also improved thermal efficiency. The GE9X introduces ceramic matrix composite materials into its hottest sections. These materials can withstand temperatures hundreds of degrees higher than traditional metal alloys while weighing significantly less. This way, the engine operates at higher overall pressure ratios and thermal efficiencies. The GE9X's overall pressure ratio is about 60:1. By comparison, early 747 engines operated closer to 26:1. The later GEnx 2B used on the 747-8 is published at an overall pressure ratio of about 44.7 at takeoff and about 52.4 at top of climb, depending on rating. Higher pressure ratios mean more efficient extraction of energy from fuel, but they also demand exceptional cooling and material stability. This is a fundamental shift in what engines can safely endure. At takeoff, a modern 747-8 engine produces about 66,500 pounds of thrust per engine. Multiply that by 4 and the aircraft has enormous total thrust available. That surplus allows flexible takeoff performance and strong climb gradients even at heavy weights. The GE9X on the 777X is in the 105,000 to 110,000 pounds of thrust class depending on certification. While the 777X has less total static thrust than the 4-engine 747-8, each GE9X produces significantly more thrust per engine. This allows comparable performance through modern aerodynamic and efficiency improvements. It also changes how the aircraft accelerates and climbs and also manages engine stress. Each GE9X operates closer to its optimal efficiency point during cruise, rather than being oversized purely for redundancy. The result is lower specific fuel consumption during long segments. Fuel efficiency is where the philosophical gap becomes impossible to ignore. The 747 was designed when fuel cost was important but not dominant. Airlines prioritized capacity and range, while fuel burn was acceptable as long as the aircraft could move a large number of passengers reliably. The 777X is designed in a world where fuel cost dominates route economics. Every percentage point of efficiency matters. Boeing and General Electric estimate that the GE9X delivers roughly 10% better fuel efficiency than the previous generation GE90 engines. Compared to classic 747 variants, the gap is far larger. These are manufacturer estimates, but real-world performance depends heavily on route, payload, as well as operating conditions. Still, the direction is clear. The 777X is designed to make long-haul routes profitable with fewer passengers and lower operating margins. Higher efficiency engines burn less fuel per seat mile and reduce carbon output. While aviation still faces major sustainability challenges, the 777X represents a step toward compliance rather than resistance. Noise regulations barely existed when the 747 first flew, so its original airframe and engine placement were not shaped around community noise limits. Over time, quieter engines and operational procedures reduced its footprint, especially on later variants, but those changes worked within a design that predated modern standards. The GE9X, by contrast, was engineered from the outset to meet the latest ICAO Chapter 14 noise limits. Its very large fan moves more air at lower exhaust speeds, while chevroned nozzles and an acoustically treated nacelle reduce jet and fan noise during takeoff and landing. For many major airports today, meeting these limits is not optional. The difference in engines changes how these aircraft feel long before anyone looks at a fuel chart. On the 747, 4 engines create a sense of constant presence. There is more background sound during climb along with more vibration through the structure and a gradual transition into cruise that feels heavy. For many passengers, this became part of the identity of long-haul travel, and the aircraft feels powerful and stable. On the 777X, the experience is quieter and smoother from the moment the engines spool up. The GE9X engines operate at lower rotational speeds for much of the flight, which reduces cabin noise and vibration. For flight crews, this also changes workload. Engine monitoring is more automated and more predictable, allowing attention to shift toward overall flight management rather than constant power balancing. The result is an experience that feels less dramatic, but more refined and controlled. The 747's engines were designed to be serviced frequently and replaced modularly. Airlines built maintenance schedules around predictable wear and tear. In fact, 4 engines meant 4 sets of inspections and spare parts inventories. The 777X reduces that burden by half in terms of engine count, but it does increase complexity per engine. The GE9X incorporates extensive digital monitoring systems that track vibration, temperature, pressure, and wear in real time. For that reason, maintenance becomes predictive rather than reactive. This does not mean the GE9X is maintenance-free. It just means the maintenance philosophy has changed. The aircraft is expected to tell operators when attention is needed rather than waiting for scheduled intervals alone. The 747's engines reflect a time when aviation handled uncertainty by adding backup. More engines meant more safety margin. It was a careful and dependable approach that made long-distance global travel possible. The 777X takes a more confident approach. Instead of adding engines for safety, it depends on a smaller number of extremely capable engines that are managed with far tighter control and precision. Neither approach is inherently superior. They're answers to different questions asked by different eras. The engines of the 747 and the 777X tell a quiet story about how aviation evolved. One was built to survive uncertainty, while the other is built to optimize certainty. And about that question from earlier, it's important to note that for decades, long-haul travel meant 4 engines and visible redundancy. Today, it often means 2 engines built for efficiency rather than sheer power. Bigger engines are now more than about the thrust they can produce. They are also about moving more air more gently. If you enjoyed exploring how these machines think about power so differently, let us know which philosophy you trust more in the comments. And for more deep dives into aircraft engineering, like the video, subscribe to the channel, and I'll see you in the next one. Every engine begins as a response to a problem. For Russia, the Su-57 emerged from the need to counter advanced Western fighters across enormous distances without the luxury of dense tanker support or overseas bases. It needed high thrust and the ability to dominate the fight if required. The engine was ultimately expected to carry much of that burden. France faced a different reality. The Rafale had to be a true multi-role aircraft. Nuclear strike, air superiority, deep strike, reconnaissance, and carrier operations, sometimes all within the same deployment cycle. That meant its engine had to be compact, reliable, efficient, as well as predictable under stress. Those requirements led to 2 very different power plants. The Su-57 currently flies with the Saturn AL-41F1 engine, which is an evolution of earlier flanker engines. From the start, this was seen as an interim solution, and the long-term goal has always been the next-generation AL-51F1 or its Délier 30. Reports from late 2024 and early 2025 confirm testing, and plans for the enhanced variant to be integrated into the aircraft. But for now, most information is available on the 41F1 that Su-57 currently flies with. The Rafale, on the other hand, was built entirely around the Snecma M88. This was not an adaptation. It was a clean sheet design created specifically for the aircraft with no intention of chasing extreme thrust numbers. And that contrast sets the tone for everything that follows. On paper, the thrust difference looks dramatic. The AL-41F1 is estimated to produce around 32,000 pounds of thrust with an afterburner. The M88-2 produces roughly 17,000 pounds. That gap often leads to quick conclusions, but engines do not operate in isolation. High thrust gives the Su-57 acceleration and vertical performance. It allows the aircraft to regain energy quickly after aggressive maneuvers and supports sustained high-speed flight when fuel allows. This is especially important for Russian Doctrine, which values rapid interception and dominance in close-range engagements. The Rafale takes a different path. Instead of overwhelming the airframe with thrust, the M88 delivers power smoothly and precisely. Throttle response is exceptionally linear and allows the flight control system to extract maximum performance without destabilizing the aircraft. In practice, this means the Rafale feels less explosive but more composed. That balance becomes critical when the fight slows and control replaces raw acceleration. It's also where the contrast becomes unmistakable. The Su-57 uses thrust vectoring nozzles that can deflect in multiple axes. At very high angles of attack when airflow over the wings becomes chaotic, the engines can still control the aircraft's attitude. This enables extreme maneuvers and rapid nose pointing, which are particularly useful in close-range combat. However, thrust vectoring is not a free advantage. It adds mechanical complexity, thermal stress, and even maintenance burden in the long term. It also shifts part of the control problem from software to hardware. On the other hand, the Rafale rejects thrust vector-based control entirely. Instead, maneuverability is achieved through its aerodynamic design and an advanced digital flight control system. The M88 engine is optimized for consistent thrust delivery and rapid FADEC controlled response. Rather than acting as a control surface, it is engineered for high pressure ratios and reliable power modulation that allows the aircraft to maintain precise handling without relying on engine-driven post-stall compensation. This creates a different kind of agility. The Rafale may not perform the same post-stall maneuvers, but it maintains energy more consistently throughout a fight. So, what do you think matters more over time? Energy you can keep or maneuvers you can't repeat? Let us know your insights in the comments below and we'll get back to this later in the video. Both these engines might perform well, but high performance is meaningless if heat overwhelms materials and control over sustained flight. Russian engines have traditionally emphasized peak output, and the AL-41F1 follows that lineage. It is built to tolerate very high temperatures and mechanical stress. However, that capability is constrained by material limits in the hot section. Prolonged supercruise or sustained afterburner use rapidly accumulates heat and increases thermal fatigue in turbine components. Specific detailed information on the exact material composition is classified, but it utilizes high-temperature components that make peak performance achievable. The upcoming Izdelia 30 is expected to improve this balance. Open-source descriptions point to higher operating temperatures enabled by improved alloys as well as revised cooling paths for more efficient thermal management. However, until the engine enters widespread service, these improvements remain projections rather than confirmed operational gains. The M88 was designed around endurance from the outset. Its hot section uses single-crystal turbine blades with thermal barrier ceramic coatings. These material choices keep temperatures under control and allow for repeated high-stress missions without pushing the engine close to its structural limits. This difference matters a lot, especially during long deployments. Both aircraft are capable of supercruise, but they approach it differently. The Su-57's higher dry thrust allows it to sustain supersonic flight without an afterburner under certain conditions, particularly with lighter loads. Exact speeds and durations remain classified or inconsistently reported, but test flights have confirmed the capability. The Rafale can also supercruise to typically just over Mach 1 in clean or lightly loaded configurations. This is not meant to be dramatic, it is meant to be useful. Fuel efficiency is where the M88 truly shines. Its specific fuel consumption is low for its class and gives the Rafale excellent range and time on station. For a multi-role aircraft expected to loiter, strike, return, and launch again, this is a decisive advantage. The Su-57's engines consume more fuel at high power settings, which is a trade-off for their thrust and maneuverability. This aligns with Russian operational assumptions where performance is often prioritized over endurance. Engines are one of the hardest parts of an aircraft to hide. The Su-57 represents a transitional approach to stealth. Its AL-41F1 engines use round exhaust nozzles, which are not ideal for radar or infrared signature reduction. Measures have been taken to reduce detectability, but this remains a known limitation. The Izdelia 30 is expected to address some of these issues, potentially with revised nozzle geometry and improved thermal management. However, specific details remain classified, and any assessment must be treated as informed estimation rather than confirmed fact. The Rafale does not aim for full stealth. Instead, it minimizes detectability through controlled emissions, lower infrared output, and careful integration. The M88's efficiency helps reduce heat signatures that contribute to survivability without radical design changes. The beauty of the M88's design is that its simplicity leads to more certainty. The M88 was designed for long maintenance intervals and modular servicing that support sustained operations during extended deployments. The engine's reliability allows planners to assume that aircraft will be ready when needed. The Su-57's engines are still evolving in service. While the AL-41F1 benefits from a mature design lineage, its integration into a stealth airframe adds complexity. Russian Doctrine historically accepts higher maintenance demands in exchange for performance, and that philosophy remains visible here. As the Izdelia 30 matures, this gap may narrow, but for now, it remains part of the equation. There is one final distinction worth making. The Rafale's control philosophy centers on system predictability and fault tolerance. Its flight control software and FADEC are designed to prioritize stable handling and controlled energy use if systems are damaged or degraded. Engine response is tightly bound within predefined envelopes to ensure the aircraft behaves consistently across pilots, loadouts, or mission profiles. This reduces pilot workload and supports complex multi-role operations where precision and reliability matter more than exploiting extreme flight regimes. The Su-57 adopts a broader controllable envelope. Its engines expand the range of recoverable flight conditions to allow controlled flight in attitudes and speeds that would normally exceed aerodynamic limits. It provides tactical flexibility but also increases reliance on engine health and precise coordination between propulsion and control systems. In the end, the result reflects different assumptions about how aircraft are expected to fight and recover. And neither approach is wrong. They simply reflect different answers to the same question of how to survive when physics stops being forgiving. Remember we asked whether sustained energy or bold maneuvers matter the most? The answer is that over time, sustained energy tends to matter more. Repeatable performance allows pilots to remain effective throughout an engagement and also recover between maneuvers. They can adapt as conditions change, but one-time maneuvers offer limited advantage once energy is depleted. So when you look at the Su-57 and the Rafale, you are really looking at two philosophies of power. One bets on thrust and future potential, the other bets on balance and reliability with repeatable performance. If you enjoyed this breakdown of fighter engine design, make sure to like the video, subscribe to the channel, and share it with someone who loves aviation.